See, people are typing. Interesting. Okay, we have people from the industry. Are there any building managers, building owners? Just curious because this topic might be interesting to some people who's kind of being directly impacted by the COVID-19. Cool. We have student energy efficiency and housing, multifamily, nonprofit, data analytics. Okay, cool. We'll start at about 5:35. Sure. I'm gonna share.
Yeah, I just saw the name Zhu Shengming. I want to say hi.
Maybe, yeah, maybe you muted yourself. You're speaking. So, Chen Xin, could you do you mind sharing our Slack channel in the chatting window to everyone, that people who are interested in some post-webinar discussion can join? Thanks. All right. I see. It's 5:35. I see people are still joining. I guess we'll just get started now as we wait for people to join. We'll post our material on our website after the event. Okay, so let's get started. Hello, everyone. Thank you all for joining this event. Hope you guys are staying well and healthy. This event is hosted by Energy Innovation Network. It's a nonprofit organization based in Silicon Valley, focusing on promoting the communications in energy and sustainability area. I know the audience here today comes from all around the globe. So again, it's a great pleasure to meet you all and appreciate all the efforts you made to join us. My name is Lu. I'm going to be your moderator for this event. I'm a volunteer at Energy Innovation Network. My full-time job is at Vertigris, an AI company based in Silicon Valley, focusing on advanced energy metering and analytics. It's been helping customers like NVIDIA, Grand Hyatt Hotel and Farm to drive down energy usage in their commercial industrial buildings. So again, I'm really excited to meet you all and looking forward to spending the next hour and a half with you all. Today, we're very honored to have Professor Xu with us. He's going to share the latest updates and some practical solutions we should know about to make our buildings more COVID-19 resilient with the least energy possible. So quick agenda, we'll spend a few minutes introducing our organization, Energy Innovation Network, and also the audience here, who you are, basically, who the audience here today. Then our speaker, Professor Xu, will take over to do the talk, followed by a Q&A session. So in the meantime, if you have any questions, feel free to type it in the chatting window. We'll collect them and talk about them in the Q&A session. Some quick note, like any other webinars you attended, please mute your audio during the event. After the event, if you're interested in joining a post-webinar discussion, we'll share link, our Slack channel and LinkedIn group. You can join us. It will be shared during this event. First of all, let's take a look at who the audience here today. As you can see, we have folks from all around the globe, United States, Canada, Europe, you know, Asia, all around. So again, thank you all. And it's really interesting and a great opportunity to exchange ideas among different countries, among different backgrounds, different perspectives. I'm really excited to see what kind of spark we'll have today. Quickly, who we are. As mentioned before, Energy Innovation Network is a nonprofit organization founded at Stanford in 2015. We're all volunteer-based, and our vision is to promote communication, technology, research, business, and policy to advance a more sustainable future. We have 18 core members now, and we're headquartered in Silicon Valley, California. So what do we do? In short form, we hold various events and conferences, big and small, throughout the year to bring people together to share ideas and resources. We host annual summits. For example, in 2019, we hosted a summit focusing on US-China energy and climate, and also artificial intelligence and energy at Stanford campus. Hundreds of attendees from all around the world joined us, and the feedback was quite positive. We also hold other events, for example, Global Clean Future Influencer Series and distinguished speakers events from industries to bring individuals with big impacts in clean energy to share ideas. We also have investor startup mixers where you will see investors, entrepreneurs, industrial experts to have some in-depth talk on the latest technology trends and potential investment opportunities. Also, we have luncheons and technical discussions where people will join for a cup of beer after work before the COVID-19 hits, of course. And then we'll have some specific topics to discuss over, for example, battery storage, microgrid, electric vehicles, and smart technologies, etc. So if you're a professional working in any of the industries in the energy and sustainability field or interested, we'd love to hear from you and see you in one of our future events. Feel free to reach out in our website. And also we have some openings. Feel free to check out in our website. Some upcoming events. So one is our 2020 Inspire Summit. So the theme is from Green Swamp to Green Opportunities. We're inviting speakers to do a TED Talk about 10 minutes each. So we still have speaker applications open. Feel free to check out the links down below. Some upcoming programs. For example, the education programs, we collaborate with professors, senior executives from the industry to offer lectures and workshops to share ideas with the audience. That there's an upcoming course called Renewable Energy Finance coming up in July. Feel free to check it out. We also have Women Power program. Okay. That's it. Thank you for your patience so far. So without further ado, let's come to our topic today. Allow me to introduce Professor Xu to you all. Professor Xu is a distinguished professor at Tongji University, China, Shanghai, China. He's also an acting director of Tongji Xin'ao Renewable Energy Research Institute. He has many experience in the energy and energy efficient and sustainable building field. Before he came back to China, he worked at Lawrence Berkeley National Lab for 9 years and received many awards during his tenure there. So he's today is going to talk about COVID-19 and the sustainable buildings. and on the latest research and findings. Without further ado, let's welcome Professor Xu to take over.
Thank you, Lu Chen, and thank you for Energy Innovation Network for inviting me. So let me switch to my share screen. You have to stop, your share screen. Okay. Okay, so today I will talk about how to minimize COVID-19 airborne transmission in new buildings with least amount of energy. And more specific, we want to ask the question whether buildings are ready or not while reopening the United States. So this is a presentation of a summary presentation for one-day workshop we hosted in March after we have some field experience in China. And this is a summary of a highlight most of the content. So I want to say thanks for these contributors. This presentation is a little bit long, probably last 40 to 50 minutes. If you want short answer, whether our buildings are ready or not, short answer is no. And I'll go through this why I think it is not ready. But if you are not a technical person, you want to skip the middle part, you can come back in 20 minutes and see what should we respond. The section 1, before I jump into the details, let's go through the transmission mechanism of COVID-19 in building environment. So this is a slide published by REHVAA, that's a European equivalent of ASHRAE. This is basically tells how COVID-19 transmitted. For example, if you have a person here in buildings and it can cough and talk, that will generate droplets. Those droplets, some of them evaporate into a droplet nuclei. And droplet nuclei is very small. It can be airborne and transmitted over long distance, affect people. And some of the droplets are really large. They will deposit on surface. It can be a table, can be a floor. And when people touch these surfaces, or when people walk by, they can stir up all those particles and people get infected through direct contact or indirect contact. And this distance is roughly less than 2 meters from here to here. That's why we call it social distancing, 6 feet. So if it is beyond 6 feet, you won't inhale droplet directly. However, all these routes still exist. Droplet nuclei still exist, and all these contaminated surface still exist. COVID-19 can stay alive for a long time because when people cough and sneeze, it takes less than a few minutes before it's reached to droplet nuclei. So the way very few people get infected through airborne nuclei is only because the dilution. It's not because the virus was dead or killed. Another route is through toilet. This is confirmed as well. So when you flush a toilet, if an infected person flush toilet, a droplet will be generated into the air. And some of the droplet will change to droplet nuclei and eventually get affected people. So there is, so far, there is no absolute evidence to support COVID-19 can be transmitted through airborne droplet nuclei over long distance. There is no concrete evidence. However, many cases, I would say, we have cases in bus and train, as well as in buildings, at least in China, from the published literature, also from the field experiment proves that live virus can stay over a long distance. And also in Europe, people found live virus on the exhaust vent surface. But all these evidence are indirect evidence. So here's a major sources. Major sources are droplet and contaminated surfaces. And this is the size. So large droplet size is between 50 to 100 micrometer. And droplet nuclei is relatively small. But many studies prove that all these viruses can stay alive in the air for 3 hours, sometimes 2 or 3 days. And this is another interesting observation in China. Most of outbreak happens in indoor space. Roughly 83% of patients who are infected happens in home between family members. This is a proof of home quarantine doesn't work. If you lock people in home, it is useful, but it won't stop the outbreak in short time period. You probably remember CNN correspondent Chris Kumos. He is infected and he locked himself in the basement, and eventually he infected his wife, his children. So if you're just locking yourself in home, it's not useful. It's not very effective. And researchers has developed various risk models. There is one risk model developed by Jiang Yi, that's a researcher in China who is relatively famous in this field. And also this is a convention model we called Wills-Rayleigh model. I'll go through this model a little bit. So P here is number of people get infected. It is 2 ratio. So C is number of new cases, and S is number of successful. So this is the chance how many people given in a building, how many people, percentage of people get infected. There's a function of these. I is the number of patients, how many people get infected in the first place. And Q is a breathing rate. And P here is, Q is a quanta, basically how much bacteria each patient generate. P is breathing rate. T is time, how long you stay in this building. And the Q is ventilation rate. You'll notice in this equation, the only thing we can control is ventilation rate. Nothing else we can control. We can't control how long people stay inside the building, and we can't control how much they breathe. So the only solution for building operators or HVAC engineers to fight COVID-19 is to provide enough ventilation. The only way is to dilute virus concentration to be low enough so it will stop the transmission. And here's some results. If you use all these models, all these numbers are calibrated against the field data we collected in Wuhan. And we calculated for outspace, for example. Where's my mouse here? For outspace, if it is a 2 meter social distance, 2 meter social distance may not be enough because it depends on the wind condition. If 2 people stay 2 meters away, social distance, and stay for 20 minutes, and if the wind is no wind, basically, it's a calm day, the wind is 0.2 meter per second, the probability of getting infected by that infected person is less than 0.2%. It is low, but just given the number of people, it's still relatively high. Thinking about if you have 1 million people, this number still be large. But if the wind is strong, for example, if the wind is more than 1 meter per second, and you talk to each other, and the probability will be much lower. So this says the beach is relatively safe. You probably see on the newspapers lots of photos of a crowded beach. People think this is a high risk. Actually, a beach is safe because the wind is strong. The mechanism behind this is a dilution. It can only dilute the virus. It can't kill the virus in short time period. And for a small office, we calculate the risk as well. For small office, if air change power is, for example, is 5.6 air change power, and if people sit in the office over 8 hours period, like a typical working schedule, and if one person in this office is infected, what's the probability of other people? So if other people is sitting next to him, depends on the distance. If we sit next to him within 0.5 meters, this is a different ventilation system. The typical, this is for displacement ventilation system. This is for underfloor air distribution. And for most of the buildings is we use fully mixed ventilation. So you have air supply at the top, air return at the top as well. So the probability is about 18% over 8-hour period. That's why we think reopen the US and let everybody go back to buildings, working office without preventive measure is high risk. And what happens if you have a building but with many rooms share one air handling unit? That's very typical system in the United States, because in the US, most of HVAC system is all air system. So one AHU system serves 10 rooms, for example. And in this room, you have red dot here is one people will get infected. What happened to the rest of the rooms? Will the rest of people get infected as well? So here we did some calculation. If the total air volume is 3,000 cubic meter per hour and duration is 8 hours. And if we don't do anything based on the current condition, we just operate as it is, operate with the return air, that's a B here. Operate with scenario 3. And fresh air rate is 30%, return air is 70%. That's a typical configuration in the United States for all air system. For in the infected room, there's roughly 10% of chance, 9.4% of chance you will get infected just staying 1 day with a patient. For other room is 1.8%. That's 2% of chance for a single day. But if you go to office in a large building and stay there for 1 month, for example, this is after 1 month, you have more than 50% of chance to get infected. And the scenario A is what happened in China right now. In China right now is people turn off all the return air system. We operate building mostly with only fresh air system. There's no return air to prevent cross-contamination. In scenario 1, and the total airflow rate is 30%. If there is a patient in this building, the chance is 23.4%. Of course, other room is 0 because it's outside air only. There is no return air. So based on this simulation and analysis, we think here, wearing mask is important inside the building. Wearing mask outside is not necessarily so important. And local filtration is important. If there's no local filtration, you can't protect buildings. And here, another thing is a pre-screen occupancy are the key. you have to make sure people who are sick or infected, they shouldn't enter the building. But now we know there's a large percentage of people, they don't show any symptom. So social distance is not enough, at least inside the building when air conditioning system is on. So here is some data we collected in Wuhan, China, and see where is a high risk area, and if there is one patient inside of the room, where all these bacteria really stay, virus really stay. And so here is a nurse dress protective suit, for example here, and after 5 hours, on the protective clothing, they find more than 1,000 virus copies. And however, they are not infected because they use a negative pressure and they use a good ventilation. Later, I'll jump into details how they design all these ICUs. And also, they make sure they have to decontaminate the floor and surface continuously. And this is a very contagious virus. So you not only should be careful with the air, but also should be careful with surface. And mostly the floor. People pay lots of attention on the tables, but the floor, sometimes they neglect. And the shoes can carry the virus accumulate on the floor over a long distance. And here is some results in ICUs. For example, the airborne COVID-19 was not detected if we use ventilation system, HVAC system properly. If you have negative pressure control and use effective ventilation. But toilet, we find very high concentration in toilet. And here, because toilet, basically there's no ventilation. And it's very small, it's 1 square meter only. And the toilet bacteria, a virus was mostly generated through breathing, or maybe from the use of the when they flush the toilet. And in hospitals, we find another high concentration area. This is, I think maybe in the US, we found many doctors and nurses infected because they didn't pay too much attention in this area. Is in the April removal room. So if a doctor and nurses, they wear protection suit, go to the ICU, take care of the patient, all this virus is going to land on the surface of this protection apparel. And when they took off the clothes, all these virus will be airborne, resuspended. And also that's the time when they take off all the mask. So the 2 suggestion is before you take off protection apparel, you have to do a whole body disinfection. You should just spray your body, the clothes, before you take it off. Maybe this is a procedure we should pay attention if you are nurses. But if you're not nurses, for example, you're just ordinary people, you still need to take care of family member who are infected. And you can't wear regular clothes if you have a family member who is sick inside of your house. You can isolate him in one room. But when you take care of him, every time you enter the room and get out, you need to wear a protection suit. That's number 1. Second is wearing protection suit is not good enough. I should be really careful how you take off all the clothes. The second part I want to talk today is how to mitigate the infection in hospitals, and how we design HVAC system, and how we design and build all these buildings. You probably read the news in 10 days. What's the details of those design? This is a mobile captain hospital used in Wuhan. This is Wuhan found out home quarantine is a bad idea. Somehow in the US or in the rest of the world other than Asia countries, people still didn't realize that's a problem. So if people show symptom or test positive, you shouldn't lock them in-house. Go ask them to go home. You should lock them in this mobile cabin hospital. This is can be built very fast. In this case, is they use a stadium. They convert a stadium into this temporary hospital. So you have a patient, for example, they have separations. You can't just lock people in a stadium with open space. The ideal case is just to separate with a little bit fence here. And this is the layout. And here we did a CFD simulation and see where is a high risk area. This is air comes in, and here's the air comes out. In the high risk area, while we're putting some local filtration fan filter unit to protect nurses and doctors. In a mobile cabin hospital in Wuhan, because all these preparation and excellent ventilation, we don't have any people getting infected. Here is one key ratio. I mentioned this key ratio several times. That's the dilution ratio. This is a number we learned from SARS back in 2003. When SARS outbreak happens, how to prevent people getting infected. We found is that if you can dilute the air, infected person, the air they exhaled by 10,000 times is relatively safe. That's the number we use. And if you can't, if it is higher than this number, it is green. Even somebody is very close next to you, you're still safe. But if this dilution number is less than 300 times, you are in high risk area. And this is a ventilation we prevented because we provided, because when we say 10,000 times the dilution, people don't have any idea how we should design HVAC system. Roughly, if it is a 150 cubic meter per hour per person outside air ventilation rate, that's the equivalent of dilute the air by 1,000 times. 1,000 times we find in Wuhan hospital, it is safe because nobody get infected. 10,000 times is a little bit extreme. That's a guaranteed safe. And we also did a preliminary analysis because conventionally we only provide outside air roughly about 30 cubic meter per hour per person in typical buildings. This may be not safe enough, but infection rate, we can control it less than 0.5% if you provide this amount of outside air. So in a typical building in the United States, it is designed as 30 cubic meter per hour. And if you reopen the US and people go back based on this analysis, the chance of you getting infected is roughly about 0.5%. And here's a strategy we use. Basically, it's a strategy we use for any infectious disease in building. You need to do three things. One thing is control the source here. control the source, and make sure if there's a patient or infected person in the room, the air he breathes is controlled. You don't let it disperse over long distance. Second is cut off the route. And the last one is protect vulnerable person. And let's see how it is implemented in building design, HVAC design. So this is Xiaotangsan. That's an emergency hospital during the SARS outbreak. They built this in 10 days. And in Wuhan, they built 2 hospitals. One is Huoshenshan, another is Leishenshan. So the Thunder God and the Fire God hospitals, they have a similar layout. We call it 3 zones, 2 corridor. 3 zones is clean zones. So that's a clean one. And another 2 is the contaminated zones when the patient stays. And the semi-contaminated zones is when the doctors and nurses come back, and there are patient rooms. You have to maintain negative pressure in contaminated zones and semi-contaminated zones, and put a positive pressure in clean zones. In that sense, you control the airflow. And these are the numbers we use. You have to use a separate and independent HVAC system for different zones. You don't mix them together. And control the airflow direction. The airflow direction has to go from here. The control the pressure less than 5 Pascal. And patient with a critical condition has to be stayed in the negative pressure isolation room with 100% outside air. So basically clean air comes in and dilute the air out. And you treat patients with moderate and severe symptoms in negative pressure room as well. Here is in negative pressure isolation room. That's a very critical rooms. Well, you have to use 2 HVAC systems, because if one HVAC system fails, you have to use the other one as a backup. Here's the layout of all these hospitals. This is a hospital for, can't remember, but I believe it's a Leishenshan Hospital, in each patient room. So here it is, for example, this is exhaust. Exhaust, unlike conventional hospitals, exhaust has to be in a lower position. So here is a patient bed here, and here is the supply. Supply can be on the ceiling, but if the exhaust is on the ceiling, you can mix the air in the patient room. So if the exhaust at a lower position, you can prevent air get dispersed in the rest of the room. So this is important. And also this is medical staff corridor. That's negative pressure as well, but not as negative as here. And in negative pressure isolation room, the supply, we use a 3-stage filtration. That's preliminary air filter, medium air filter, and HEPA filter. The virus content of patient in the severe and critical condition is roughly about 1,000 times higher than mild patient. That's the amount of virus they generated. So if you mingle them together, then you can't spend most of effort to control the most of the virus. And replace and disinfect filters every 10 days. In Leishenshan, actually they didn't do that because after 10 days, there are just fewer and fewer patients. Here, another thing is for negative pressure controlled room, because it is negative pressure controlled, there will be a patient in the room. You have to install air filter at return air outlet. And here is another criteria we use is for the exhaust and supplier vent for the building, because all the air has to be come from outside and all the exhaust is going to go outside. You have to maintain a certain distance. Based on the design code and requirement, a horizontal distance is should be more than 20 meters and vertical is more than 6 meters. In Huoshenshan, actually, people construct all this vent at a height of 15 meter. I'll show some pictures later. Because we know the bacteria or the virus can stay alive for a long period of time, can be up to 2 or 3 hours in the air. So we want to make sure all this exhaust, this is a plume we simulated. All these exhaust won't go to the atmosphere and carried away by the wind. Otherwise, other people exposed to the outside maybe get infected. This is to prevent the long distance infection. And here is what we did this. So here is the layout of this temporary hospital. There is a building 1, building 2, and intensive care ICU. ICU is we need to pay special care. So this layout is important. Make sure it's on the correct the wind direction, because you don't want to the exhaust from ICU eventually pollute other area. So this is pressure gradients in typical patient room. This is in Huoshenshan Hospital. This is a fire guard hospital. You can see the patient room is a negative 15 Pascal here, and the buffer zone is a negative 5. The contaminated corridor is a negative 10 Pascal. This is roughly. And we pay special attention to the toilet room. Toilet room is the highest, is a negative 20 Pascal. And another thing we need to be careful is the supply air rate. Supply air rate in these hospitals is much higher, and we exhaust way more than supply. The exhaust air exchange rate is 12, but the supply is 8. That's how we created negative pressure. ICU, because there's 1,000 times more bacteria generated per patient. That's why the supply air rate is 12, exhaust rate is 24. That's a very high number. 24 is level clean room for semiconductor industry. And exhaust air rate is 3,000. And here is also the pressure control as well. And we use lots of high efficient, high pure filter in all these rooms just to filter out all the virus. Now here is the interesting part. The first time people see all this picture, they think this is a chimney, which actually is not. This is an exhaust vent. For each individual rooms, for example, all these rooms, patient rooms, they don't have their own exhaust. All the exhaust are centralized into this chimney-like exhaust vent. The top of this is 9 meters above the ground. I make sure it's high enough, and the virus is diluted. And also, all this air, before it's exhausted, it has to went through the high temperature chamber. Basically, you just burn all this virus dead, and also HEPA filter. This is a wind analysis. Let's skip this part. Okay, So maybe the second part you would say, oh, nothing to do with me. This part is something really to do with you. Just in buildings, how we operate and HVAC system with the least amount of energy, especially in the next few months. And the strategy we use is maximum, these are principles. The strategy is maximize the outside air ventilation for dilution. The key is the dilution here. The cross-contamination can be only controlled if you dilute the air enough. And you can use air filtration as well. The temperature and humidity control is useful, but you can't, the temperature and humidity, all this virus won't stay alive a shorter period in high temperature and high humidity condition. That's why in summertime, the outbreak is less severe than the winter time. However, the temperature and humidity control itself is not enough. And local cleaner is important. We recommend FFU here is a fan filter unit. Fan filter unit is quite popular in China, but it's hard to get fan filter unit in the US. In China, because people use fan filter unit to control PM 2.5 in the last few years. And screen the people who enter the building and open windows. Open windows is also prevent or increase the ventilation through dilution. Social distance is important. And here is another thing is recirculation. Make sure all air system, you have to turn off the return air. That's particularly important in the United States, because in the US, most of the office building, they don't have operable window. The window is sealed, you cannot open it. All the ventilation is provided by the HVAC system. So you have to turn off the return. If you turn off the return, you might increase your energy consumption because you just bring in too much outside air. And maybe you lose a little bit of the temperature control. The temperature, if it is really hot, your office temperature can be a little bit higher. But we think is the price worth to pay. If you want to use the return air, you need to install filter on the return air. It can be either HEPA filter or can be MER 16 filter. And the fan coil unit is a little bit controversial. In China, people think it's okay to use a fan coil system because the fan coil system is not a large system, it's an individual system. And there's no cross-contamination if you use a fan coil system. But in Europe, people recommend you turn off fan coil system at all because fan coil system still can disturb the air and resuspend the virus deposit on the floor or on the table. So fan coil unit with operable window is you have to open all the window. Although open the window will increase your heating load or cooling load in summer, but still worth to do it. Without operable window, you need to install temporary mechanical ventilation in open area in the corridor because these are high-risk area. Lots of people come to open area in the corridor. And you can use a fire protection smoke control system to increase ventilation. This happened in China in last few months. People just turn on the smoke exhaust system during off hours during night to provide enough ventilation to dilute out all this virus. This is a typical system we see in the United States. Probably use all air systems. Use all air system if there's a multi-zone system, you need to be especially careful. Multi-zone system is quite popular in the United States as well. And because the virus can spread through the return air. Right now, we are not too sure virus will die during the process. In the simulation, it shows it won't, because it takes less than 2 or 3 hours for virus spread out in the buildings through HVAC system. And as a precaution, you should use 100% outside air. If it's a dual fan system has many advantages because the ductwork is kind of large. You should just use as much as outside air as possible. Another thing we need to be careful is heat recovery system. Many buildings has heat recovery system, unless it is a two-coil system. In Europe, people recommend just turn off all the heat recovery system, because heat recovery is try to recover the energy from the exhaust, and through heat recovery device is HRV. Cross-contamination always happened, whether it's a paper plate, rotary well, and the metal plate. In US, people recommend you can still use it, but in Europe and in China, even metal plate, we don't recommend to use it. And the transportation terminal buildings, these are also very important. For example, the airport, the train station, because here is a large number of people concentrated, and this is a place we want to dilute the air as much as possible. And here's the criteria we use. Airport is less than 600 ppm during pandemic period. This is the number we recommend. If there's a recovery period, for example, right now China is in recovery period is 850. In a railway station, the number is a little bit higher because just too many people are in railway station. So here's the, and if people are not familiar with HVAC ventilation control, in normal building, we control this to be less than 1000 ppm. So 600 ppm just decreases number roughly by half. So how to use air filtration? Everybody knows air filtration is important. Everybody knows outside air dilution is important. But how to use this with least amount of energy? There is a few ways you can do that. One way is use a local purifier. You don't filtering all the air, but for example, earlier mentioned, for the open area, you filter the air. And also if you have a critical important offices, for example, CEO offices, you filter the air as well. Another thing is a low energy intensity one is the UV lights. You can put a UV lights in the air ductwork, and also you can use a UV light just in the open space. It can be a ceiling suspended mounted. And this COVID-19 pandemic also, we learned some hard lessons, because in the old time or the traditional fashion, when we design HVAC system, we seldom consider the health issue because the number one concern is energy. That's the title of this presentation as well. We always think how to build and design an HVAC system with the least amount of energy. And now we learn that maybe health is more important than energy. So, but how to balance these two things? For example, if you use 100% outside air, definitely the health condition will be better. but it just wastes too much energy. So we think here is some consideration in future if you design or build or retrofit HVAC system. For example, you need to reserve space in HVAC for extra air filter, UVC unit or disinfection. You don't necessarily install all these filters right now if there's no pandemic, but at least you need to reserve the space because in the last few months, we found in China it's really painful to install air filter on the return ductwork. There's just simply not enough space when we design all these buildings. And another thing is a reserve space for emergency response. You can rearrange building layout and occupants if something emergency happens. And minimize air distribution, airborne transmission. That's in United States, that's a very, I would say, severe problem for that. Because labor costs in United States way higher. So people tend to build large HVAC system. For example, if you in San Francisco, many office buildings, they have only 2 or 3 air handling units for the entire building. The air handling unit is just huge. The fan can be taller than me. Now we realized maybe many small system is better than one large system. One large system, the maintenance cost is small because you can hire just one engineer to maintain one large system. But if you have multiple systems at multiple floor, maybe you can control the contamination better. And so in future, if we design a HVAC system or construct a HVAC system, we need to think about normal operation plus pandemic condition operation. For the temperature control, for example, temperature control, you have to provide adequate temperature control. But if you leave a little bit of room, so you can control the temperature a little bit higher in winter or lower in summer, and during pandemic period, at least you can turn on 100% outside air. So leave a little bit of space. And the energy storage as well. If you have energy storage in building during the pandemic period, it is also you can use the energy storage as a backup heating or cooling source. And independent control of temperature, humidity, we found it is important as well. If you separate ventilation from the temperature control during this pandemic period, you can improve the ventilation. You can double or triple ventilation without sacrifice the temperature. And also there are some other hard lessons we learned as well. For example, number 6, air filtration. Ideally, you should have a filter on the return air for all buildings. But if you can't, you should save the space for the pandemic operation. Number 8 is also one detail, and but we learned this in the hard way as well. The sewage disposal of the sewage disposal of condensation water. Normally we neglect that when we build a building, but during the SARS and also during this COVID-19, we find if you don't use a separate riser for each floor, the virus can be spread out through a condensation water pipe, because condensation water pipe eventually will link to the sewage system, and sewage system is has lots of airborne virus through the toilet because they are not covered with water all the time. And if the air handling unit, for typical air handling unit, the cooling coil section is in negative pressure, and all these virus can go up from sewage system and go to the air handling unit and eventually spread out in buildings. Okay, so all the 3 parts, all this technical content, and here I want to talk about some everybody can understand some layman word. So in second wave, where are the high risk area of buildings? So at least if we can't save the world, at least we can protect ourselves. And in Wuhan, people did research. They collect air sample in Renmin Hospital, various locations of the hospital, as well various locations of outside, and see where is a high risk area. Also, researchers collect the air sample in this stadium, mobile cabin hospital. Here's some results. If you think outside is safe, you probably get it wrong. So for example, here we found, sorry I didn't translate this into Chinese, in English yet. The first one is basically a small 7-Eleven market outside of a hospital, and at the door, not inside of 7-Eleven, but outside of 7-Eleven. That's the highest concentration. And outside of a hospital, that's at the entrance of the hospital, that's a high concentration as well. But inside the hospital and in the school and in the supermarket, it's zero. So because of ventilation control, because of pressure, negative pressure control. And here is also some data for various locations. This 19 at the top here, that's a toilet. Toilet has very high concentration. This 42 here, that's where people take off protection suits. That's very high concentration as well. So be careful with this location. And another thing is we should be careful with all places, especially the indoor places with a high concentration of people. This is a study I did in a prison, because in a prison, the same thing happened in the United States. A total of more than 200 people get infected in this case study. And we want to see why and how to control it. Because prison is a high concentrated area. In China, typical is 20 people in a male cell, 12 prisoners in female cells. And they provide only small vent. It's less than 25 centimeters. That's for security reasons. And we calculate the CO2 concentration under various wind and temperature condition is roughly about 2032 at the bottom here. 2032 is about twice as much as 1000 ppm standard. So if you don't prevent adequate ventilation, you put people in high risk. So if you go to a train station, if you go to a shopping mall, just be careful. Make sure all these spaces provide enough ventilation. So here's a summary of today's talk. Sorry, my mouse today doesn't work properly. And so far, this is findings we have. So 2 meter social distance may not be enough, especially inside the building. For outside, it's okay. Inside may not be enough. You have to wear a mask. And airborne COVID-19 are not detected in ICU and CCUs. That's just an evidence of, if you're very careful with HVAC system, you can prevent this from happening. And a relative high COVID-19 is happening in toilet, also in the medical staff area. Section 2 is reduce hospital transmission. Home quarantine doesn't work. You have to lock people up if they show moderate or test positive. And a separate hospital in 3 different contamination control level, and use the pressure as a tool, use a different pressure level. And a centralized exhaust air outlet. You can't have many exhaust in hospitals. For a public space or public buildings, you need to screen occupants before they enter public space. In China, we have this cell phone app. It shows a red, green, or yellow, different color. Everybody has a QR code. Before you enter a building, they're going to scan it. But that probably won't happen in the US for a while. And try to avoid air mixing, okay? And turn off return air, maximize outside air ventilation, and pay attention to toilet. In Europe, they specifically mentioned you have to turn off the windows for toilet, close the window in the toilet, and run the fan 24 hours, turn the fan. In that way, you put a toilet in negative pressure. Otherwise, the contaminated air in the toilet will disperse to the other area. And use FFU for high-risk area, and make sure you dilute the air enough. Maybe this is too much you can memorize, but here, what you can do to protect yourself. Are you ready for the second wave? First one is everybody need to wear a mask. You have an N95, that's the ideal. If you don't have, at least wear a surgical mask. Second is you have to open the window. And if you have a choice, you should try to sit next to a window. And you should limit the use of public toilet. There is it's called criteria. It's called ASHRAE criteria. It's called as low as possible. Since there is no benefit to use public toilet, you could be infected. So just try not to use public toilet. If you go out, try to use private toilet in your home first. Just try to avoid any public toilet. And fan filter is useful. And on the return air, you have used MERV 16 at least. And get PPE. That's important as well. Get yourself ready. Because if second wave does come, it's very high chance your colleague, your family member, or somebody you know may be getting infected. At that time, you need PPE. Here's some statistics, very interesting. So in Wuhan altogether, there are more than 3,000 doctors and nurses are infected in Wuhan. However, later, additionally, 42,000 doctors and nurses were sent from other provinces to help Wuhan. All these doctors and nurses, none of them get infected. So PPE is very useful, very effective against COVID-19. Just read this number. There's no people getting infected among all these 40,000 doctors when they come back to Wuhan later. And learn how to use PPE, where you should take it off, and how you take it off is also very important. Well, if you still can't remember all these, just remember this. The concentration of CO2 is a very good indicator for you to know where is a high-risk area, where is not high-risk area. If it is lower than 550 ppm, it is safe. Even there are patient or infected person in that building, in that room, fairly close to you, you're still okay. But if it is more than 1,000 ppm, the risk is very high. So one way you can do this is to maybe just buy a CO2 sensor. It's not so expensive, and I think there's still plenty on Amazon. So whenever you go to a place, you want to know whether it's a high risk or low risk places, just check the CO2 concentration. Of course, if you don't have sensors, just use your nose. Normally, if CO2 concentration is higher than 1000 ppm, the smell is not so pleasant. If the smell is not so pleasant, just go away. Just don't stay there for a long time. If you can't remember the rest of my presentation, just remember these two numbers. I think that's all my talk today. Thank you for listening. And now we can move to a Q&A session.
Yeah, thank you so much, Professor Xu, for bringing us this, such a informational presentation. We've got some questions. Let me just quickly share my screen. Yeah, I'll stop your screen right there. So we've collected some questions while from the chatting window and also from a pre-event survey. So question one is from the audience here, and ask in scenario 3, are buildings advised to use certain types of filtration to reduce the infection rate?
Yes. Maybe let me go through all these questions and just one by one. Yeah. I can read it so we don't have to transfer back and forth. So in buildings should use a HEPA filter to reduce infection rate. If you don't have HEPA filter or HEPA filter resistance is too much for your HVAC system, you should use at least MERV 16 or higher. Second question is, can we be proactively detect how ready we are? Yes, just use CO2 sensor for a given space. You measure the CO2 sensor. That will tell you how much outside air you prevented to that space, whether you have enough dilution in that space. Third question, does humidity level in room has impact on contaminant control? Yes, in winter it is important. We find the virus survive longer at the low temperature and low humidity area. So if the humidity is low, it's simply the virus can stay alive longer. But that's not a problem in summer. Summer, normally the humidity level is too high instead of too low. That's a problem only in winter. How long do we expect this guideline to be followed? An example for the year, or it's hard to say, or is there a minimum period? I think as long as we don't have vaccine, or as long as the pandemic is not over, we should follow this guideline to operate our big windows. At least that's my own opinion. All the guidelines seems expensive, go against energy efficiency. How should people balance using less energy and follow expensive guidelines? Should we give up energy efficiency totally? No, it's not. All these guidelines seems expensive during the pandemic period. For example, if you use outside air, if you turn off air heat recovery systems, your energy bill will go up, but only for this month or next month when during the pandemic period. So there is a balance here. That's the strategy I mentioned. You should design the building as much energy efficient as possible, but you need to leave some buffer zones. You need to leave some buffer zones for space. For example, the outside air ductwork cannot be too small. Normally, we design it as 30% of the total air, so the ductwork is small. Actually, we should enlarge that duct to 100% outside air. So make it possible we can do 100% outside air. That will not increase your energy bill during normal operation at all. So that's the strategy we use. You need to balance these two things. And first one, last one, should we be careful when do outside hiking, running, or biking? 6 feet enough? From our model, the risk analysis model, outside hiking, biking, running is safe. With or without mask, you are safe. You you don't really need mask if you stay outside. Mask should be used inside the building, but somehow people think it's relatively safe inside. So when they get inside the building, they take off the mask. That's just, we should do that reversely. 6 feet is enough for outside.
Yeah, thank you, Professor Xu. There's also some follow-up questions on the chatting window. Can you see them in your screen or?
Okay, sure.
There's a question from Sunny. What's the best way to disinfect the surface of projects and of objects and people? Can ozone disinfection be applied?
Well, COVID-19 is a new virus. Nobody really knows. There's not enough study. But for surface, or the soap, alcohol, or the decontaminate agent right now are proved to be effective. For the air, we know UV is effective, and filtration is effective. And also the dilution. Dilution is the most effective way to reduce the risk.
Right. There's a question about CO2 again. I guess that's a very interesting point that you mentioned. That this audience says why CO2 concentration matters that much, maybe.
Okay. Yes, because the only way to reduce your risk for airborne infection is through dilution. In the first part, I presented the mechanism of how the air spread out through the air and how people get infected through the airborne transmission. It's hard to kill it, and they stay a long time for 2 or 3 hours, so you have to dilute it. If you dilute it, the CO2 is a good indicator how much air, outside air, you bring to the space. So that's why CO2 concentration matters that much. That is the only indicator. Also the most effective indicator we use.
Mm-hmm. So there's another question saying, would the practice of passive building design need a major revision going forward to take care of the health of the occupants first instead of the energy efficiency of the building? I think it comes back to one of your points, right? Where
yes.
we optimize liquid energy efficiency prior to the healthy.
Yes. So passive building design, they put a lot of effort on insulate the building and prevent the leakage. So they use very high quality windows and also very high quality installations. But for example, in passive building design, there's no single item, as far as I know, on windows, they have to be operable windows. I think all these things probably need a revision, and that's another reason is why healthy building is getting popular as well. Healthy building design, I think, probably need all these things. Just how to prevent adequate, enough, or even more than enough ventilation during high-risk period.
Yeah, there's this next question is also related to the passive house design. Do you think there's a secure way for healthy?
Yeah, they don't have to contradict with each other. A building can be a passive, can be a high efficient building, but also can be very efficient or very secure, very healthy during pandemic period, as I mentioned. So the building should have the capability to provide a large amount of outside air or a large amount of ventilation, but you don't have to use it during the normal operation. I think that's the key.
Great. There's the next question is in the former research paper on COVID-19 virus transmission rate risk versus CO2 levels. Is it proportional, nonlinear?
No, there is no such paper because COVID-19 is really a new virus. There's just so many things we don't know about it. So now all these risk factors, all this is based on the some field data. We just run backward the model and calibrate the input of the model. We're not too sure all these input are accurate or not. And we don't know whether it's proportional, whether it's linear. We only know where it's safe. For example, we think it's 10,000 dilution ratio is safe. Maybe 5,000 is good enough. We don't know about it. Only thing we know 10,000 is good. But if you, for economic reason, if 5,000 is as effective as 10,000, you should go for 5,000, right? But we just don't know about it.
Okay, thank you, Professor Xu. The last question, I think, don't you think CO2-based DCV is a balance between reducing virus transmission risk and energy efficiency and should be promoted?
Yes or no, because the CO2-based DCV, when this was built or designed, use a DCV system, is now mostly for energy reason. So the ductwork is not large enough to provide high outside air rate. That's the no part. But the yes part is CO2-based DCV. At least you have a CO2 sensor, so you know what's the ventilation condition inside of the building. Because for most of buildings, and I would say 90% of buildings, there's no CO2 sensor inside of the building, and people don't know they provide enough ventilation at all. For example, for some conference room, if you go there, you know instantly they don't have enough ventilation because you stay conference room after 2 or 3 hours, you feel uncomfortable and your face is getting red because the CO2 concentration is too high. These are high risk area, just you shouldn't go there, at least in the next few months. So I think the key here is that DCV has a CO2 sensor, so that's good. But DCV, the ductwork design is not big enough, that's bad.
Oh, there's a last minute question. Is there any white papers on forecast on how post-COVID might impact building energy usage?
Nothing I know of. But I'm thinking is probably won't impact building energy usage at all, because most of the buildings are existing buildings. Every year, we don't build too many new constructions. The energy level, intensity level in buildings probably will be as high as before, as low as before. Won't change too much.
Interesting. There's the last question, I think. What if only outdoor air cannot satisfy cooling demand when recirculating dampers closed in summer? Do you have any advice about it?
Yes, that's a good question. So when we design HVAC system or construct HVAC system, engineers try to play on the safe side. So they oversize the coil, they oversize the chiller a little bit, a chiller maybe 2 or 3 times, but the coil can be oversized by 50%. So we found in China, most of buildings, when they turn off the recirculation damper, the temperature is a little bit higher, a few degrees higher, but not that bad. And also in winter actually most of the building can maintain satisfied temperature. So that's a good part to be over capacity. But in the US, we are not too sure. But for building operators, they can just test out in their buildings. For example, right now it's very hot. They can just turn off their circulation damper and see what happens. And also they can pre-cool the building. You can run the system. For example, if people comes at 9 o'clock, normally engineers turn on the system at 7 or 8 o'clock, 1 or 2 hours in advance. But during the pandemic period, maybe they can run the system 24 hours, or they can turn on the system at midnight, at 12 or 1 o'clock in the morning, use 100% outside air. So pre-cool the building before occupants comes.
Yeah, thank you, Professor Xu. Is there any other question from the audience here? I guess I'll take that silence as a no. Okay, thank you all for joining us, and thank you, Professor Xu, for bringing us such a wonderful presentation. We've learned, I mean, I myself learned a lot of information today, right? It's definitely a challenging time for everyone, right? Especially building facility operators, or even just occupant, right? Or you're just shopping at a nearby supermarket. It affects all of us, right? And some industries are hit so badly. For example, the hospitalities, right? Many of them are closed during this pandemic. And also, Professor Xu mentioned that the jails are also like a very vulnerable area. Overall, we hope this video brings you some useful information, could benefit your work and life, provide some guidance to you and your family wherever you are. Take care and stay well. Last word, if you're interested to join the post-webinar discussion, we have a Slack channel. You can we'll look forward to seeing you guys there. Okay. Thank you all. Stay healthy, stay well. We'll see you next time.
Okay. Bye.
Bye.